Hello everyone, hope you are doing great. Well, in this video, we will see how the empirical equation that fits the black body experimental curve given by Planck led to the idea of quantized energy, an idea that also helped in the explanation of the photoelectric effect. Now coming back to the black body radiation, let's first understand what a black body is. It has been thermodynamically observed that objects exchange heat in the form of radiations. A body that can absorb all the radiant energy incident on it as well as can emit all the radiant energy when heated is called a black body. Although a perfect black body is still a theoretical concept, there are nearly perfect black bodies like the carbon black, the famous black holes, and the new famous Vanta black. A relation that gives the amount of power radiated by a black body is the Stephen-Boltzmann law that states that the power emitted is proportional to the fourth power of temperature, where P is the emissive power of the body, sigma is the Boltzmann constant, and T is the temperature of the black body in Kelvin. Now let's come to the actual problem that troubled scientists for a long time, the spectral distribution of a black body radiation. In this experimental observation, when a black body is heated, it has a pronounced peak at a given wavelength for a given temperature. When the temperature is changed, the peak shifts to a new wavelength. This is the reason why objects appear brighter when heated more, like heating of iron, when iron changes its color from red to white. Wien's displacement law relates the peak wavelength to the given temperature of the body. The lambda max is the peak wavelength and T is the temperature. The product of these two quantities is a constant. Wien also attempted to obtain the expression for the black body radiation curve using thermodynamics, but his formula was valid for shorter wavelengths only or higher frequencies. Then Rayleigh tried, and his formula was valid for large wavelength only and failed badly for shorter wavelengths, although there was a numerical correction that was provided by genes. This flawless work failed to fit the experimental curve. Then came Planck. Now Planck tried to fit this curve and he assumed that the exchange of radiation with matter is in multiples of h nu. He assumed that the matter resonators have energy in multiples of h nu and obtained the following relation for the black body radiation known as the Planck's law. In this expression, the average energy epsilon nu of each resonator is quantized. The term n nu d nu is the number of modes per unit volume in the frequency range from nu to nu plus d nu. This result was also obtained by S.N. Bose, who communicated his work to Einstein in 1924. This led to the development of the Bose-Einstein statistics. Interestingly, if we rewrite this law in terms of wavelength, we can reproduce the Rayleigh-Jeans law and Wien's law. Now, if we consider a function f lambda given by this, for two limiting cases, the short wavelength limit and the long wavelength limit, we obtain the Rayleigh-Jeans law and the Wien's law. The Rayleigh-Jeans law, which was valid for long wavelength limit or low frequencies, if we put lambda very greater than hc upon kBt in the above expression, f lambda becomes lambda kBt upon hc, which leads to the Rayleigh-Jeans law. Similarly, if we consider the above expression, the Planck's law for short wavelength limits and higher frequencies, and we put lambda very less than hc upon kBt in f lambda, we get the Wien's law. Therefore, the Planck's law of black body radiation. This law is a universal law that was built on the idea of quantized energy. Hope this sums up all about the black body radiation. For more detailed analysis, read Thermal Physics by Garg, Bansal and Ghosh. Thank you. Have a nice day.